At long last, we come to the Gaussian process regression model and how to do inference in this model. Now, as usual, in regression, we have some observed data at some x's and xi's and yi's that are observed, and this model is no different. So let's write down, we have some x's, and let's actually break them up into x1 to xl, and xl plus 1 up to xn. And for notational reasons that will become apparent, you may already be able to guess why. Let's say that we observe yl plus 1 up to yn. So these are observed. And we'd like to get the posterior predictive distribution on the y's corresponding to x1 up to xl, given these y's, given yl plus 1 up to yn. So we want to get the distribution on these y's, given those. So let's call these, following our notation to fit with our notation in the previous video, let's call these y's yb, and let's call these ya. So here a and b, just to be, maybe to be clear, a is going to be 1 up to l, and b, l plus 1 up to n. All right. So I said the posterior predicted distribution, but under what model? Well, as usual, we're going to have some random variables. I'll stop writing all the intermediate ones. Well, maybe I'll write them for now, just to be clear. No, okay. So you get the point. So that's, we're going to have y1 up to yn. And what distribution are we going to put on these random variables? These y's are obviously going to model their corresponding these observations, and these are unobserved. Maybe I should make that clear. These are unobserved. So these are not actually necessarily values that these are taking. We're going to use this ya to denote possible values that these random variables y1 up to yl could take. Okay, so now we need a distribution on these y's, and what are we going to take? Well, we're going to use a Gaussian process to define this. So we are going to take z, let's say zx, to be a Gaussian process, which I'll abbreviate gp, with mean function mu and covariance function k. So it has this positive semi-definite kernel. And then we're going to look at these. For each x here, we're going to consider the value of this Gaussian process at that x. So this is a GP on our d. I didn't say, but I should have said. These x's are going to be, well, actually, I guess they don't even need to be. Yeah, they don't even need to be on RD. These can just be in some arbitrary set S. So this is a GP on some set S. And these y's are going to be in R. And now, so we still haven't defined the y's. What are the y's? Well, the y's are going to be yi, let me use yellow to be consistent. Yi is going to be zxi plus some random, some Gaussian noise, epsilon. So epsilon now, so epsilon is going to be a vector, epsilon 1 up to epsilon, what do we need? N. Epsilon is a multivariate normal with mean 0 and covariance matrix sigma squared I. And epsilon is also independent of, so this is epsilon is independent of our Gaussian process Zx. Okay. So this is our model. This is the Gaussian process regression model, and note that this S is just some arbitrary set. So this is, boom, this whole thing, this is our model. And now what do we want to do? In order to do inference, we want to get the posterior predictive distribution on these random variables y1 through yl given these observed values. These are the observed values. So let's write down what we want. So we want, for inference, maybe I'll put inference. So that was the model. This is inference. So we want to get this. We want to get P, YA given YB. And this also, of course, depends on X's. But let's just drop the dependence on X's because these are just some fixed, these X's are just some fixed non-random things. These aren't random, so we don't need to include them in our probabilities. So what is this thing? Well, this is where the key step in our calculation in the previous video comes into play. So in the previous video, we talked about how we had this setup where we had this Gaussian vector z and this Gaussian epsilon. We added them together, we got y. And then we were able to figure out what the conditional distribution on ya given yb was. So what's the corresponding thing here? Well, we have this yi plus zxi plus epsilon, so this looks very similar. And in fact, we have y, the vector of y's, this is y, let's call that y, is equal to, let's call z tilde, the vector of z's, plus this vector epsilon. So this will be, let's make a little space for it. Let's make a little space here. This let's call z tilde, so we don't get confused by thinking that it's our Gaussian process. So z tilde is just this vector of random variables that the Gaussian process, the finite dimensional distribution, this vector at these finitely many points. And so we have this. And now we're back in the familiar situation of just having a multivariate Gaussian. We have this z tilde, because zx here, this family of random variables, is a Gaussian process. Z tilde is a multivariate Gaussian. That's just the definition of a Gaussian process. And epsilon is, by definition, also a Gaussian, and they are independent. They are independent. And so we are just back in this nice simple case, well, somewhat simple case, simpler case, y equals z plus epsilon, except it's z tilde now. And so we get the distribution here. So what do we need? We need to get the K matrix and the mu vector for z. So maybe let's first do that. Epsilon here is just the same as below. So let's figure out what the mu and K are here. Well, we want to get the distribution. So we have z tilde, maybe let's switch. Z tilde, we know, is multivariate Gaussian, and let's call its mean vector mu tilde, and its covariance matrix K. And mu tilde, this is just the vector of means of these random variables. And what is that? Well, the mean of this first one is just mu of x1, right? That's the definition of using the mu, where mu is this mean function. That's the definition of the mean function for a Gaussian process. It gives you the mean of each of these random variables. So this mu is just mu x1 up to mu xn, where mu is our mean function. Let's make that transpose just to make it a column vector. And what's the K matrix? What's the covariance matrix of this z tilde? Well, it's just using the kernel of this, using the covariance function of this Gaussian process. It's just K evaluated at the pairs xi and xj. That's the definition of, because the covariance matrix is just the matrix of the covariances between zxi and zxj. And the covariance of Zxi and Zxj is from the formulation of the Gaussian process is just that kernel evaluated at those 2 points. So the covariance matrix is this K, where Kij, maybe I'll put, let me rearrange slightly. Let's call Kij the kernel evaluated at xi and xj, and then K will be the matrix of Kij's. And let's partition this into K, or maybe I'm jumping the gun. We'll come back to that in a second. Okay, so we're getting in pretty good shape now. We've got this z tilde. We have our y is z tilde plus epsilon. Remember, we're trying to get this posterior predictive distribution. That's our ultimate goal. And so we're going to use the key step here. We've got our K matrix. We've got our mu vector. Let's, mu tilde now, whatever. And so now we know from this earlier video that the distribution of y is this, with mu tilde here. And we know immediately, we did all the work before, that this conditional distribution is this normal with mean m and covariance matrix D. So let's write down what this is. So we have this. Let's maybe define what these mu a and KABs are and all. So we have mu tilde, we can break up into mu tilde a, and, or maybe let me just call it mu a. So simplify life a little bit. Where of course mu a is just mu x1 up to mu xl. That's following this earlier sort of notation. And we can also break up K into the block matrix, just like before. KAA, KAB, B, KBA, KBB. Okay. And we know from here that the conditional distribution of ya given yb equals little b is this guy, is just this. So that's what we wanted. We wanted this posterior predictive distribution. So we know that, let's use a color, ya given that yb takes the observed values yb. Remember, we had these observed values yb, and this, the conditional distribution of this, is normal. That's so, in other words, this probability is the density of a normal with the following mean and covariance function, mean vector and covariance function. So this is equal to, we have our answer. This equals normal density evaluated at ya with mean m and a covariance matrix D, where they're just exactly, so I've chosen the notation so that everything works out perfectly here. So I'll just copy and paste, just to emphasize, since we had some slight changes in notation. Actually, let's move down here first. Just to emphasize that this is the formula. These are the formulas that we wanted. It is exactly this. Okay, so we've got it. And that is literally all there is to it. Let me just clean this up a little bit. That is all there is to it. So that is how to do inference in the Gaussian process regression model. How to get the posterior, in particular, how to get the posterior predictive distribution, which is the main type of inference that you're interested in. And so maybe I'll make a couple remarks about how you would actually use this in practice? Well, if you're just interested in visualizing this posterior distribution, if you're interested in making predictions, like maybe you had, draw some data here. If you had some data and you're interested in getting the values at some new, predicting values at some new points, something like this, well, then one thing you could do would be to just plot the curve of this posterior mean, or you could plot the mean just at those points, but you would get some, maybe some curve, something like that. And that would be okay for just visualizing this, but that's just sort of the most rudimentary application, because you're not really taking advantage of the fact that you've got the whole posterior distribution. You've got the whole shebang. So a more intelligent thing to do would be to actually, a slightly more intelligent thing to do would be to use, to indicate maybe with some error bars or something. So this is going to be small error here, bigger, and then it's going to be small, bigger error. You could use some error bars, something like that. But even still, that's just really, I mean, it's good for visualization, very good for visualization, to see what the posterior distribution looks like. But the best way, the best use of this model would be if if you're really going to use it to make a decision about something, if you're going to have to decide something, then you should choose a loss function which is appropriate for your application, and then you can actually use the full power of this posterior distribution to minimize your expected loss. So that would be the most intelligent use of the fact that you have a whole Bayesian model here. I mean, that's a nice thing. So you should use that to do what you actually really want to do. So that's how you do inference. And so what did we have to choose? What decisions did we have to make in order to apply this, to set up this model? Well, basically everything is determined by this formulation, except for this mean and covariance function. So these are your parameters in some sense. These are the choices that you can make. And also, I mean, you could also, this is sort of a, less important parameter, but the main thing that you're choosing is this mean function and covariance function. And you can choose these, using your domain knowledge about the particular application that you're doing a regression for. You can choose these mean, and especially the covariance function. That's really most important, perhaps, to fit, or to make sense for the application that you're considering. And it's cool that you can actually even have certain constraints on the functions that you're willing to consider, like they have to be symmetric or periodic or blah blah blah. And you can actually use your domain knowledge about what you want the functions that you're using for regression to look like in order to govern this Gaussian process. So that's a nice thing. That's a very nice thing. And of course, you could always choose these to give you the same, choose the kernel that corresponded to the Bayesian linear regression kernel that we derived earlier. And so this all generalizes Bayesian linear regression. Now this Gaussian process for regression is, in some sense, this is a really extraordinarily useful tool, I think, and it's perhaps the most powerful general purpose tool, the most useful for applications, general purpose tool that we've talked about so far.